I'm going to start right away because there's a lot of things I want to cover and not much time. So, well, I will not spend too much time introducing myself. I just want to say I'm a creative coder, I'm a multimedia artist. I do a lot of things with TouchDesigner. And if you're curious about me, you can, of course, always check my Instagram, or you can also check my website, where I have some projects and I explain over there some of my things. So let's not waste on that. Check that out later if you feel like it. And let's dive right into it. So I'm going to give you a little overview of what we're going to see. So today we will be focusing on cellular automata. I will do an explanation of these systems in 3 different dimensions. So we will start with 1D, then move to 2D, and finish with a 3D implementation. So in more detail, what we're going to be doing is pretty much what we see here. We're always going to start with a chapter, so a subject. In this case, we start with a 1D version of it. Then we will check some principles or some information that is necessary to understand them. Then we're going to focus on a particular aspect of that system. So we start with elementary CAs. And CAs stands, of course, for cellular automata. And to begin with, I'm going to give you some introduction to it. But the formula for the workshop would always be that I explain you the principle of how things work. We live code a simple version of that system, and then we move on to explain the general version of the system. And the general version, we are not going to live code because that takes too long, but usually it's just a tiny bit of difference from the simplified versions. All simplified versions will be live code because that's how you get the best understanding. In the sample files that you can download, it's all in there. I recommend, though, that you follow along in the live coding sessions because that always makes it better to understand. And I must say also that I put together some things yesterday night, so some things may not work in the files that I shared, or something maybe typo somewhere or some weird things. I will do a better version of the file for those who are gonna join the Patreon. Unfortunately, I couldn't do it today, but you will find an updated version later on with more links and more information. Okay, so let me begin first by giving you a brief introduction to cellular automata. So what are they? They are basically a system that you can imagine as a grid. Okay, so imagine that you have a grid, and the grid has 2 different states. It can be dead or can be alive. In this workshop, we will represent the live version of them with a white cell and the dead version with a black cell. So in this system, you can see it's a 7x7 system. And we see that only one cell is alive. And this would be the cell that is alive, and all of them are dead. So that is pretty much how a system works, in this case, in 2 dimensions. Okay, so they are discrete systems. So that means that they are numerable and finite. And like I said, you can imagine them as a finite number of cells in a grid. They are abstract in the sense that they can be defined purely mathematically and then later implemented by some physical means. For example, in this case, we're using a computer and we will do some computer graphics with them. But you can also do it with as originally was done by some of the researchers, with a game of Go and some little pieces, or any other way you can imagine to actually make them work. So it is abstract in that sense, that it can be abstractly defined, but can be applied in different circumstances. And it's also a computational system. And this is one of the most interesting aspects, which is that these CAs are capable of solving algorithmic problems. And they can even emulate a Turing machine. So that means that they are general purpose computers in some sense. And some of them can have these universal properties. That is really fascinating stuff that I encourage you to dive into later after the workshop. I will provide some links for that, so yeah, you can check it. Now, another view of the algorithm, how it works, is basically we always will define a set of cells in a grid, and we need to access those cells with some addresses. And then we check the neighbors of the cell. So in the case of a cell here, the neighbors will be the ones that are immediately next to it, horizontally, vertically, or in a in a circle around it, sort of square around, yeah? Okay. Then we define rules based on the neighbor states, and then we update the current cell. And we repeat that in a loop. That is, in a nutshell, what all these algorithms do. And it's quite simple in that sense. Okay, let's see. Now, another thing is that CS systems display complex emergent behavior, even with extremely simple principles. And to understand that, you can think of the phrase, the whole is more than the sum of its parts. And another important thing about why I wanted to show this workshop is that CAs are the perfect gateway to dive into complexity. And complexity is the study of complex systems. So what that means, I will try to explain as we go along. But the key concept of this is that you start with simple rules, something that you pretty much understand completely. And then after some iterations, you end up with something very complex that was not the same that you started with. And CAs are a perfect example of that. All right, a very brief history. The first cellular automata system was invented by John von Neumann, who is this person here. He was looking into the problem of self-replicating machines already at that time, at the very beginning of computing. And actually, John von Neumann is the one person who designed the current architecture of computers that we still use today. So his system had 25 different states. It was relatively complex, and it was already capable of self-reproduction, already at that time. So he basically figured out that information could be used in two ways. One can be interpreted by the self-reproducing machine and use as instructions to build a copy of itself. And two, the copy does not interpret information, but is passed along to that entity, to a new entity. And the surprising thing is that that's pretty much how DNA works. And if you think about it, it is crazy that von Neumann did this because the description for the double helix structure of the DNA was discovered only in 1953. So that's pretty amazing that he came up with this before the discovery of the DNA. And then his system was also the first discrete parallel computational model. And now I said here WinCat shaders because a parallel model is what we're going to use, capable of emulating a universal Turing machine. So this is pretty crazy stuff. I encourage you to dive into that a bit further. I provide here a link where you can read more about it. It's in your file. And further on, after John von Neumann, we have these three individuals who focus a lot in research. The first one is John Conway. He is famous for the game of life. Second one is Stephen Wolfram. He has been researching cellular automata, specifically the elementary versions and more advanced versions, even a unified theory of the universe with automata from 1983 onwards. And finally, we have Christopher Langton. He's famous for the Langton loop and some cyclical CAs, I think. And the Langton's ant as well. Here's some links for that. So as you see, there's a rich history of cellular automata. Now, let me tell you briefly why I think they're interesting. The first reason is that they are perfect gateway to complexity theory, as I mentioned. Second, they really make you think quite intensely about reality, the universe, and computation in general, given what the implication of the systems is. Three, they are a perfect application for parallel computing, so they are a great way to learn shaders and to do things with shaders. And four, they create fascinating patterns that can be expressed visually, which is perfect for wonderful software like TouchDesigner. Okay, some terminology before we dive into the code and explaining how this works is an automaton. When I say automaton, I mean one single cell. An automata is the collection of cells, so the whole system. Those are the automata. A lattice is a fancy word for a grid. Neighbor is just a cell that is adjacent to the current one. A neighborhood, we're going to see different types of neighborhoods, but in general, it's just the addresses of all the possible adjacent cells in the system. The state is just the value that a given cell holds. It can be a 0, can be a 1, can be others, as we will see. And alive, when I say alive, I always mean that it has a state of 1. Remember that it's important. And when I say dead, it always means it has a value of 0. We will see many other states, but only 1 means alive and 0 means dead, all right? Okay, we will come back to that quite often. So first, some principles about GLSL that I want to discuss before we write code. So just as a refresher. So I'm going to create here a very simple noise stop. Oh, I see I have my, how can I get rid of this? Okay, I have a cell as noise stop, sorry. Let's make it 5 by 5. I'm going to make this to be colored, just so you can see what we're looking at. And we're going to use this to explain the basic principles of GLSL that we require for the workshop, okay? So first, I'm going to explain you what texels are. I'm going to make this base, connect it here with an input to my noise. And we're going to see what these texels are. I'm going to create a pixel shader, and let's start writing some code here. All right. So the very first thing that I want to explain is that we need a way to address each one of these cells. That is the core knowledge that we need in this workshop. So I'm going to create here a uniform, and it's going to be an IREC2. I'm going to call it the address. And we're going to use this to access each and every one of those cells, okay? So let's create this. And I'm going to here, first of all, declare the UV coordinates that you probably are familiar with. So these are UV coords. They go in the range from 0 to 1. And we're going to create some color just to see something. So if we use the UV coordinates to check our color, then we will use them here, right? So we look at the texture, and these go from the range from 0 to 1. So if we do that, we're gonna get, we're gonna end up seeing, oh, there's an error, that's an error. But we will end up seeing our image here, okay? But that's not what we want to do. I want to address each and every one of these cells via my uniform. All right, but if I use numbers from 0 to 1, that becomes very hard because I have to start typing here a calculation of what the center of the pixel is in this normalized range. Then I have to divide 1 by 5. Then I have to divide that by 2 to find the center. So it's a lot of floating points calculation that we don't want to do because it's a bit too complicated for that, and there's a better way to do it. And that is using texels. So in this workshop, we don't use normalized, we don't use UV coordinates ever. We're going to use texels, which are simply a way to address the grid, but with integer values. So this is floating point values. And texels are integer values. And they are much more simple to think of because if you see this, they already behave like a grid. If you see in TouchDesigner, when you press D on this shader, you see that we have X and Y values. Those are in essence the texel coordinates that we need because this is 0, 0, 1, 0, 2, 0, 2, 0, 4, 0. And if we go to the end of it, it's 4, 4. I hope that you understand why. It's just the coordinate system with integer values based on the resolution of this texture. So that's way easier to think of. That's why we're going to use them. And how to define these texels? Let's, for example, use this here and access this with our address. But we're not going to use texture to access it. We're going to use texel fetch. Texel fetch because we're using texels. Fetch because it's a function that allows us to access those texels in the texture that we want. So if we do this, then suddenly now you can see that I can address each and every one of those colors with my address using this texel value. So now, right now, I 0, 0. I'm on the bottom left. If I say 1, 0, then it will be 1 to the right. So because 0 is the row and the first value, the 1 is the column. Now I'm in column 1, row 0, which is this pink column. if I would like to see this last color, then it will be row 0, or let's say column 1, 2, 3, 4, 0, 1, 2, 3, 4, sorry, and the same for the row 4. So if we say 4, 4, then we are on that pixel. Okay, that is one of the principles that we will use over and over again, this construction, pixel fetch and some pixel add. Okay, now let's duplicate this. And now we're going to explain, I'm going to explain coordinates inside the shader here that we just made. Oh. Okay, so what I want to do now is the same thing as before, but instead of passing an address, I want to know the texel coordinate of each one of these pixels. So let me erase this. So in order to do that, I'm going to define here an array 2xy, and this is going to be the texel coordinate for each pixel. And we're going to fetch it in the shader itself. So we can do this in a couple of ways. For example, we could create resolution information. So this will tell us the resolution of the shader. In this case, it's 5 by 5 size. And we can also get our UV coordinates as before. And then we can compute the XY by multiplying the UV coordinate by the resolution. But remember that the UV coordinates are float values, and the resolutions are also now defined as float values, even though they come here as integer values. But because of this multiplication, just to be sure we have the right information in texels in integer form, remember texels are integers, we cast them to this, and then we pass them here. And there's an error here, again, color, therefore, and then we have a copy of it, because indeed we are now accessing each texel coordinate for the pixel. However, there is a simpler way to do this, that we don't need all this stuff. We can simply define our texel to be instead this, because there is an already built-in variable that we can use. This GLFrac for XY is already all this. Okay, so we don't need that. We can simply do this. And it's the same thing, all right? So this is the construction that we will use. Yeah. Texels for each. All right. Okay, and now one last thing about GLSL that we need to know before we implement the 1D version is about structs. So just using the same thing we have here, a struct is a structure in GLSL that looks like this. We're going to call this struct cell. This is going to be in every single implementation we're going to look at. And here we're going to define an XY and a state for the cell. So a struct is just a way to encapsulate some information in a comfortable way. And then, since we have this information, we can basically access each one of the cells in our grid. So to access it, I'm going to declare now, if you're not familiar with structs, this is how you declare one. I have declared my struct cell that has these two objects inside. And you declare like this, cell, I'm going to call it C. And then I can define its XY value, C.XY, which is this, with the XY that I calculated here. And then I can define its state with some variable that I want. Maybe I want to do this. Maybe I want to fetch this, just the R channel. And that's going to be the state. And I'm going to define color to be basically just the information about that state in the system. Oh, no color. So here, important thing is I define it as an int. This is important, it's a common error that you probably will do when you see the CAs. We declare as an int, but this comes as a float, of course. and I'm picking only the R channel of this texture. So I'm gonna cast it to an int, and then that should be okay. Yeah. And here we don't see anything. I'm not sure what I did one. But anyways, that's not important. There's no waste of time on that. This is the important part, the struct cell. I hope the struct instruction is clear. Sorry, I'm going a bit quick, but I see the clock and I just want to right away do our first implementation. Okay. Now, some principles about the elementary CAs. That's how we're going to start. We're going to do a first explanation of the principles behind. Maybe I should see the chat a little bit. Maybe it's going too quick or something. But let me know. Someone can tell me somewhere if it's going too quick or you don't understand anything. If that happens, anyways, you have the files. And yeah, let's just keep going through rather quick. So in the simplified version we're going to build now, we only count the neighbors of a cell and not the cell itself. And remember, we're going to look now at a 1D version of our automata. So it's going to be really like this table. We're going to be looking at a cell and the neighbor on the left, the neighbor on the right, and we're going to find what states they are in, so what values they hold. And it could be the case that I am alive, so the cell that is here is alive, so it's 1, and the neighbor on the left is dead, and the neighbor on the right is dead. And that will look like this. So as we saw, this is the live state, and the black is the dead state. So if we think about this little basic system we have here, we can see that there's some options for how we can arrange the cells. And remember that in the simplified version, we only are going to count the neighbors, and we're going to omit completely the cell itself. So if we do that, we see that the neighbors of a center cell could be basically, the left one could be dead, and the right one could be alive, or the left one could be alive, and the right one could be dead, or both of them are dead, or both of them are alive. That's all the possibilities we have. We don't have any other options for it, right? And then we can see, okay, what happens to the cell, to the center cell, when those two neighbors have these states. For example, here, we can decide that when the left one is 0 and the right one is 1, so if we're looking at a cell, we will see that this guy is dead and this one is alive, then maybe the center cell becomes dead. And these rules we can make up ourselves. For the next case, maybe the left one is alive, the right one is dead, then we chose that this one is alive, and so on. So we have something that looks like this, 0, 1, 0, 1. Okay, but what are all the options for how we could arrange these numbers? Is there a way that we could do this systematically? So how can we do this in an ordered way? So if you think about it, this looks an awful lot like a binary number, right? 0, 1, 0, 1. So we can define them. For example, rule 1 could be 0, 0, 0, 0. So we can say that if this arrangement happens, then in the first case is 0, in the second case is 0, all 0. That could be one rule set, right? A second rule set could be the same, but maybe in this last case, it becomes 1, and so on. If you keep doing that, then you realize you have all the binary numbers from 0 to some value. So we notice that we have two possible states per cell, dead or alive. And we have, as we saw, a total of 4 combinations of numbers. So that means that we can create a total of 2 to the power of 4, so 16 different set of rules. And don't worry if that is not immediately clear. Why? It has to do with how we will map the values later on. But as we write the implementation, it will become more clear, okay? So in essence, like I said, 2 states, 4 combinations, that gives us states to the power of combination options. And here is a little Python script that you can use to come up with all the binary numbers from 0 to that number of combinations. So let's just run this. And voila, you see that we have here all the binary numbers from 0 to 15 listed, right? And this is what we will use to build our elementary cellular automata. our first 1D example. Okay, I hope that this makes sense. Now let's dive into writing the code, the first code. Okay, so the first thing we're gonna do is basically create a shader, GLSL, pixel shader. We're gonna put here a null. And to create a cellular automata, we need to check the states of the cells one time step at a time. So that means that we need a way to see in the back. If we start at one state, we need a way to see back in time one step. So in order to do that, we can use a feedback loop here, like this. And we're gonna put whatever constant here. It doesn't matter what you put, because we're gonna feedback this value here. Okay, I mean this node here. Now we created a feedback here. Now, just for to make things simpler, go to common, pixel format. I'm gonna make it 32-bit float. That's a bit overkill, but just so we have enough numbers, we don't have to think about it, because we will be using texels, remember, and they go above 1. So we need to have more bits to represent that in the shape. Okay, that's the basic setup. Now we can go and implement this. So let's write our pixel shader. We will start first by doing the things we already did before. So like I showed in that GLSL primer, I said we need a pixel. So we're gonna access the pixel like this. Okay, so we have a pixel. Then we're gonna define our structure, which is a cell. So we're gonna use that struct idea of a cell, just like I explained. And we're gonna define here the XY and the state of that cell. So this is gonna give us the position, and of course, if it's alive or dead, we're gonna store it in the cell. So then we're gonna create here a cell, of course, and then we're gonna assign the values to it. So XY is gonna be just the pixel of the current coordinate, let's call it, pixels. And the state is gonna be something that we're gonna define. For now, we can say that the state is gonna be 0. So it's gonna be dead at start, just to initialize this. And now we need to define a way to create the very basic first state. So in general, traditionally, for the CAs, you always choose, for example, the middle cell of the very first state. Let's make this a little bit smaller, the resolution. So let me make this to be only of size 31/16. So we have I chose a odd number here so we can have a center cell. Okay, so the center cell, let's say it's alive and all of them are gonna be dead. So we're gonna choose that to be the first state of our CA, okay? So what I mean is that the C state, we're gonna say if some initial condition occurs, so we're gonna create an initial condition here. We're gonna call it reset, so it's gonna be a reset button. And here I'm gonna create a reset uniform and maybe link this to a reset button on the parent layer here. Let's create here a reset button. A pulse, let's say, reset. Okay. So we have a reset. And whenever I press the reset, I want this system to go back to the very first state, which, as I said, will be everything black except for the very center, the center cell of the very first row. We want that to be the only one that's going to be alive. So we're going to say here, if that reset is bigger than 0, we're going to make that state to be alive. But we need to find the middle, the center of all these grids. So to find the center, we're going to say, we're going to check the XY. We're going to check the X position. That's what we're interested in here. And then we're going to see if the resolution of the shader, we're going to find its center. So to find the resolution, I also explained, you can do this. W, and we're going to use the x-axis. And we're going to cast this to be an integer as well. And of course, we need this to be half the resolution. So if that's the case, then we're going to make the state to be 1. If not, we're going to make it to be 0. Okay? So, okay, so there's an error here. It says here, cannot cast from int to bool here. So we cannot do this check. So this is a Boolean. So let's just do this. So this should be int like that. Okay, not this. All right. We don't need this time. My bad. Okay. So if we press reset, if we're running, okay, hold on. I don't know if I'm, oh yeah. If we press reset, then this needs to be updated. So let's just pass here the state of the cell here. And then we see that indeed the center has now been being set to alive. But now we also need to choose that the middle of it is alive. Okay. So if reset is 0 and the c dot the y is equal to 0, then we have set that one to alive. All right, now we have it. Let me make it a nearest pixel so you can see. So this is going to be our initial state. That's how we're going to start. And if this is not the case, then we're going to do something here. We're going to check the neighbors. Right? So that's how we're going to begin. Maybe let's make it even simpler. Let's just make this to be, for now, just the y, just the y here. So we don't need to reset it because anyways it's going to work. We're going to see all the steps. In this case, so we don't need that reset, okay? So let's omit that for now. And let's now see how we can check the neighbors. So make a function called check neighbors. And here we're going to pass our cell, the cell that we'll find here, C. All right, so let's check our neighbors. And this is going to be defined as a function with an in-out cell C. And in-out is basically a construction that allows me to pass a variable, write to the variable, and the change will propagate outside of here. Okay, so here we need to sample our neighbors. Basically, we already have information of the current cell, so we just need to find a way to ask these cells which one is the neighbor on the left and on the right. And that is quite easy if you think about it. So let's first create, we're going to find here the states. So we're going to find first the coordinate for our neighbor on the left. So that will be clearly, remember, we're going to use I vector because we're using integer values. We're clearly going to have to say, we're going to look into the left side. So into the left side to see the left one, right? And we're not going to do 0 here. We're going to do the previous state. We're going to look back one state. So if we step one time in time, we're in the second row, we're going to look back in state. So one below. That's why this is -1. So this will be the left address for the cell, right? And then we basically are in the current position for the cell. And we need to add this to the current position of the cell so that we can move left 1. All right, so that's how we're gonna pretty much access it. And now we need to use texel fetch, like we saw in the thing before when I was explaining texels. And this is gonna be equals 0. And we're gonna use that to access it. And we're gonna use 0 here. 0 because texel fetch requires you to do a level of detail, but the level of detail is 0, is all, the whole thing. And we just need the R value because it's just a simple integer that we're interested in, the state of the cell, right? So if we do that, we need to cast this to an int like we saw because this is going to give us a float. And basically now we have the left state of our cell. And now we can just copy this to get the right state. The right state will be 1 instead of -1 here. That will be the right state. And now we have an address that we can use. So, or addresses that we can use. And we have the values on the left and on the right. And then we simply need a way to store those states. States are going to be the CL and CR. Okay, those are the 2 states. And now we're going to need to check the rules. All right. So in order to check the rules, we're going to have to figure out a way to define what the rules are, like we saw when I was explaining the principles, remember? So how do we do that? So basically we need to see if we remember the principles. Recall that we had in the very simplified example, we only had four possible slots for the rule set. So that means that we need to create here a situation where we have 4 different values. So what I'm going to do is I'm going to create an array called int rule. And this array is going to be composed of 4 integer values. And here we're going to pass the rules. We need to define somewhere the rules first value, the rules second value, so 1, and the rules third value, 2, and the rules fourth value, 3. Okay. However, keep in mind that we need to know as well the right indexes for these rules based on where we are at. Okay. Before we do this, though, let's define our rule set. Like we saw before in the principles, we saw that our rule set is essentially this, all these binary numbers. So for now, just for the sake of clarity, let's do our rules in this way. I'm going to define the rules. I'm going to copy them from here, which I have them defined, so it doesn't take too long time. I just copied this into an array with 16 rules. So it's just an integer array, and we have all the rules stacked up. And you can see here rule 0, rule 1, rule 2, rule 3, etc. Now we need to access these rules. And we saw that, for example, if we would like to access the first rule in this set, this will be correct. But for the second rule, we need to add a step in size because rule 0 will always be this one, right? If we want the second rule will be this, then we need to add 4 to this, and so on. So we're going to create here a little offset to do that. So let's create an offset here, I times 4, because that's our step that we need to take. And this I is going to be the index that we want to access. So the rule, basically the rule that we want to access. Or maybe let's just call this rule, okay? It's not here. I know, but we cannot call the rule because we have the rule 4. So let's just leave it as I. But this is just the rule number with us, okay? And now we need to add those offsets to our things here. So instead of 0, this will be just L. This will be L plus 1, L plus 2, and L plus 3. Okay. And this should be so far so good. Let's just check for errors. 65. Because it's missing here something. So here we're going to pass a rule. So we can say new rule. And I'm going to create a uniform here. We're going to call it uniform new rule. It's going to be an integer. Okay, so now we have a function so far so good. And via this new rule, there should be a vector here. We're going to use the rule set, so let's just ignore that. Here we're going to pass the rule that we're going to loop in this table, 0, 1, 2, etc. So now we just need to apply the logic of the system. So let's check, for example, if these states are equal to the situation where the left one is alive and the right one is dead, then we do something with the logic for the cell, with the state of the cell. So I'm going to define here an int b 0, so the value for my cell. If that happens, then I'm going to apply from the rule that we have here, the first element, and so on. Now let's see if the one on the right is alive, then I apply rule 1 of the set, right? Then if the one on the, or both are alive, then rule 2, and finally we can say, oh, let's just be explicit, just so you don't get confused. 0, 0. If both are dead, then we apply the rule number 3. And finally here, we are going to apply that value to our cell state. And if you do that, you immediately see something has happened here. There's something going on. And let's try now change. And that's really pretty much all the elementary system. That's all there is. And believe it or not, this is actually harder than the general version. So you have done already one system. And let's explore now a little bit the rules. We know that we have 16 rules. So let's start with 0, rule 1, rule 2, rule 3. Rule 3 is super cool. So we're going to leave it at rule 3 and check out the amazing pattern that has formed. And this is remarkable because the system, as you can see, is extremely simple, very short, and it only basically uses the information from the 2 cells adjacent to the starting point, and we have already some structure that looks like this. And that is why cellular automata are so fascinating. So, yeah, that is the basic version, the simplified version. I'm quickly going to see in the chat, there's some comments about this. Oh yeah, someone already found out. Yeah, all looks good there in the comments. Perfect. Oh yeah, thanks. Shagatai, I figured it out. And yeah, let's keep going. I think I don't see any comments about anything strange. All right. That is how you make the elementary system in 1D. And this is the simplified version, like I said. So let me now show you how a complete version would look. And we're gonna do a couple of changes, but like I said, this is in fact, the simplified version is slightly more difficult to implement than the general version because of how we have done it. So now let me step back a little bit and go into a topic that we need to understand before diving into the total version. By the way, if I'm gonna start going a little bit quick as well because of time. So all this information I'm giving you about systems in one dimension, I also have tutorial videos in YouTube, in TouchDesigner. So pretty much what I'm telling you with little bit detail, a little bit less detail perhaps, but it's already online. So you can check that later. I will put it on the links. If what I'm saying here goes a bit too quick, I just want to jump as soon as possible into the more exciting ones in 2 and 3D. So that's why I'm gonna pace a little bit the thing a little bit quick. Okay, so let me see. For the complete version, we're gonna do a couple changes. The most fundamental change is that we're not only gonna count the neighbors now, but we're not gonna count all of them. So the neighbor on the left, myself, and the neighbor on the right. And how that will look like is pretty much the same. We work with the same principles that we just saw, 1 for alive, 0 for dead, and we organize them like this, yeah? Okay, the only difference is that now the table, if you compare it to the table we had before on the simple version, has grown because now we have way more possibilities for how we can arrange those cells since we're taking into account the center one as well. So that could be that the left one is dead, the center one is dead, and the right one is dead. The center one is me, so the current cell. Let's just call it current cell. And that has increased the number of combinations we have to 8. As you can see here, you can try it yourself to come up with all of them. You cannot come up with more than this, but that's certainly more than the 4 we had before. So it is natural to think that a rule set now will be bigger, because if we apply the same principle as before and we say a rule set arbitrarily could be for this first state, 0, for this second state, 0, for this third, and so on, and we fill it in, then we realize now we have 8 different slots where to place our conditions. So that means that with these 8 digits, we suddenly have now more space for binary numbers, right? We have now 8. So applying the same formula we saw before, since we have 2 possible states per cell and a total of 8 combinations that we can do here, then in reality we have 2 to the power of 8, so that's 256 different sets of rules. And if we do the same script as we did before, but we replace the combinations with 8, then now we have all these binary numbers that we can apply. That's a lot of binary numbers. And remember how we did the last version? That would be a pain in the ass to write all of them here and to search them and so on. So we're not going to do that because that's why we're programmers. We also want to be lazy sometimes. So the best way to do it is using a table, but a lookup table of a different kind. So in exact words, a texture. We're going to do a texture lookup. So we're going to step back, we're going to jump a bit back, and we're going to talk about this mysterious base that is floating around in your sample files called encoding. This encoding, it holds the most fundamental aspects of all the systems, and it deals with how to encode information for them. So typically, for all the 1D, we're going to need to encode everything to binary or to some base number system. So let's first look at the binary dots here. And we see that the principle is, like I said, we convert from a decimal value to a binary value. That is the principle. Now, I have made here for you a little script. So, like I said before, if we run the script, which is failing now because of this, okay. If we run the script, which is failing again, okay, because this should be that. Sorry. Yeah, I rushed yesterday a bit with some things. So, all right, here we have the table. We can convert it like this, right? Convert it to binary, then to a chart, and then we have a texture that looks like this. So I'm stacking the groups of rules from bottom up. So we see the very first rule here. That's 0 for all of them. The second rule is 1 for the first one, So that's really the combination of this is just the in decimal form 0, 1, 2, 3, etc. to 256. And here we have all the rules, but in a texture. So that's much handier for us. Okay, so check that out. It is not very clear. However, we don't need to do all this conversion. We can do it also straight away in a top, do it directly in a top. And here's the code how to do that. As you see here, we use a little formula that I mentioned before to calculate how many states there is, and simply just do it like this. That's way more convenient. I'm not going to explain how that works because that's you can read it, right? Okay, and then you end up with the same. Well, we're going to use this texture lookup in our 1D system. So let's see how we can do it. I'm not going to live code this to keep things quick, but I'm just going to show you what changed so you are aware of everything in there, okay? So let's see. What changed is that we have created basically this rule set, this rule generator, and oh, I forgot to mention the last one, of course. There's a generator, and this generator is able to give me, using the formula, all the states for whatever system I have. If I say 8 states, it will give me all those. If I say 2 states, it will give me only those. We need 8 states, but just so you know that this is a general purpose binary translator, okay? So that's what we're going to use in the 1D system. Sorry, I'm jumping a bit. That is this rule generator, which spits out the texture, which are all the rules, remember? And the setup is exactly the same as we had before. Nothing has changed here, nothing special. I'm just cropping here the rule that we're looking at. And the rule that we're looking at is in here. So we're going to look at rule 30, which is a very special rule. And I will explain later on if there's time why. Okay, so in here, what has changed is that instead of defining all those, maybe I should open this too so you can see the differences. Yeah, so the difference is that instead of defining those rules in this way, like that, we have them, of course, defined now in these textures, this texture that comes here. So we don't need that anymore. That's why it doesn't appear here. Then another difference is that we, of course, are looking now at the left, just like we did before, left, right. But we're also looking at the center one now. So we have added that one. So that's different here. And then the rest is just basically what's logical. So check the state. Then instead of 2 states that we need to check here, we have 3 states, of course, because we have left, center, and right. And we do something clever. So which is we sample the rules in this way. So we create an array of ints, and the rules come from the texture, and the current rule is passed here. Okay, that's all that is kind of new as well. And then we simply do the same as we did here, but for all the cases that we want. And the order of these cases comes from, I took it from this page, from Wolfram. So this order. And I did that so that we can replicate and see that we did things correctly, okay? So yeah, that's pretty much all the differences that there are here. Maybe one little addition I did as well for you is that you can initialize the system in 2 different ways, if you see here. You can use, oops, yeah, you can use center cell, which will be the case that we're using for. You can use a random at the beginning. That's why this hash is here. Create some pseudo random number. So if you do that, you can start either from the center cell with a value of 1, or you can choose random cells with some probability to start 1. And then you start to have some interesting patterns that can emerge from that. Okay. So you have these 2 modes to play with. And like I said, this is the general version of this. I have done a couple of other things, like inverting or flipping it because as we saw, the convention seems to be to start from the top and go down. So I have done this so that you can check in the Wolfram page, if you want, all the rules and double check that this works. So I'm just replicating that loop for you, so it's easy to see that it's working if you want to implement it yourself. So here you see, for example, the type rule 90, then we have the exact same result as in the Wolfram page. Okay, so that would be the elementary cellular automata in one dimension, all right? Okay, let me quickly see the chat. Okay, amazing, nothing strange there. Now, what I want to do now is maybe I should check quickly the Totalistic simplified version, because we're already 1 hour in almost. I think we're already 1 hour in. So let's do that very quickly, and then we'll do a break, okay? So let me explain you the principles for a totalistic approach. This is a different way of doing the automata. So in a totalistic version, we see that we have the same situation where, again, we're not going to count the neighbors. We're going to omit the cell in the center. We're just going to ignore that one. And we're going to focus only on the neighbors. But it's the same principle. Alive and dead, everything remains the same. And the only difference is that now we are going to look at the sum of the values. Okay? And here I think I made some mistake. Yeah, sorry, here it should be 1, 2, 1, 2. So here we see that we have all these values, and the sum of these, of the left and the right, because we're not going to count the middle one, the one on the left and the right, the sum is 0. The sum of left and right in the second case is 1, and so on, right? So if basically we have a number possible states that we can use. And there are versions where we can also count the cell itself. So basically, this is a slightly different version of how to compute the neighbors. Because instead of looking at a rule set, we're simply going to look at one single value, which is the sum of the values from the center set. Yeah, so we're going to look at one integer value. So let's assume that we have, in reality, this should include the center cell, maybe for this example, but okay. We're going to still use the binary rule sets, but now we're going to see, like I said, that they are going to be defined by a number, which is the sum of the cells. So that is the main difference in regard to the elementary CAs. So let's look at encoding again for the totalistic version. Okay, so in the encoding for the totalistic version, this might get a little bit difficult to understand, but let me try to explain it kind of briefly. We can use a formula to compute how many states we can have based on the amount of neighbors, the amount of states that we want, and the cells that they are involved. Because in this version, the totalistic version, is still 1D, but it's a totalistic version. Like I said, the sum is what matters. So here we're going to use arbitrary k-ary sets. So that means arbitrary number systems. Okay, we used binary before. Here we could use, for example, ternary. We could use quarterly or fifthly, pentately. I don't know how to say that. But the principle is that in this state that we're looking at, we have, for example, if we have 3 neighbors and 2 possible states per cell in this binary system where when we implement, then the minimum we can get is 0. Because 0 plus 0 plus 0 is 0. And the maximum is 3. So 1 plus 1 plus 1 is 3. So if we have 0 to 3 options, we have 4 possible states, right? Okay. How to compute? The formula to compute how many combinations we have is like this. We have n neighbors, we have the states, possible states is k. Then we have the total of possible states, which is n times k minus 2. That gives us the total possible states. And then if we elevate k to the power of s, then we have the amount of required digits that we're going to need to use to represent all the rules in that system. Okay? A little bit abstract maybe. But let me try to demonstrate with a practical example here. Like you see, this is a system with 3 neighbors. Then it has a system of 2 possible states like before. Then we have the binary digits like we just saw. However, we can also define different possibilities here. Let's see, for example, the case where we have only 2 neighbors and 2 states. Then our rules have decreased drastically. Maybe we have 3 neighbors and 3 states, and our rules drastically increase. So this exponentially grows like crazy because of those factors too. So if we see already with a relatively small system like this, 3 by 3, we have 2,187 total codes to explore. So that's a lot more than with elementary CA system. So yeah, don't put numbers that are too crazy here because they're not going to work. So if I do 5, oh no, it's going to crash. I think I should not have done that because it's going to crash. The number is just way too big to compute here in TouchDesigner. Okay, I think since this is crashed, and I managed to squish in a little explanation about this totalistic thing, it's good to make a little break. When we come back, I'm going to explain again totalistic as we implement the version, because this totalistic way of view is going to work the same for the 2D and the more complex versions. So if we understand the totalistic implementation properly, then it's going to be easy to do the further ones. All right. Okay, so let's do now a little break.